The functional performance equation is a new powerful tool for understanding, measuring, and improving the performance of ball milling circuits. The ball milling circuit consists of the ball mill, the pump, and the hydrocyclones. A very interesting observation about ball milling circuits is that operating them at high circulating load ratios makes them much more efficient. We can produce 2 to 3 times the amount of new product size material by operating in closed circuit with a circulating load of 300 to 500% than we can in open circuit. The question is, why? Observation of the size distributions in and out of the ball mill for circuits at high circulating loads versus lower circulating loads tells us why higher circulating loads are more efficient. The size distributions in and out of the ball mill in a circuit with high circulating loads are coarser than those operating with low circulating loads. We can do this comparison looking at the performance of two circuits with the same feed size to the circuit and the same product size out of the cyclone overflow. The one at 500% circulating load produces approximately 262 tons an hour of new finished size material, whereas the one with lower circulating load produces only 203 tons per hour. That's an increase of 29% at the higher circulating load. If we look at the size distributions going in and out of the same two mills, the mill with the high circulating load has about 71% of the material inside the mill coarser than the P80, whereas the one with the lower circulating load has about 55%. This is also an increase of about 29%. The reason why the mill is more efficient is because it contains a more proportional amount of coarser material. We can define for a given grinding circuit the overall classification system efficiency. It is equal to the percentage of coarse material inside the ball mill. That also represents the percentage of our energy that the mill is using grinding the coarse material. To carry out functional performance analysis of a grinding circuit, we make the following definitions. Coarse particles are those that need to be ground further. Fines are those that have already been reduced to the desired product size. And we typically choose the P80 as the size to distinguish between coarse material and fines. For any ball mill circuit, we can state that the production rate of fines or new product size material has to equal the power applied to the coarse material multiplied by the grinding rate of the coarse material per unit of energy applied to it in the mill. But we know that the power applied to the coarse material in the mill is the total power times the percentage of coarse material in the mill, or the classification system efficiency. We can therefore write the simple equation that the production rate of new fines or product size material for the ball mill circuit is equal to the total mill power draw times the classification system efficiency times the mill grinding rate of coarse material. Also note, by dividing the mill grinding rate by the ore grindability and multiplying again by the ore grindability to balance the equation, we are left with the ratio between the mill grinding rate of coarse material and the grindability of the same material in a test mill. This ratio between the mill grinding rate and the grinding rate in the standard laboratory mill is a measure of the ball mill grinding efficiency. So we can finally write the functional performance equation, that the circuit output of fines or new product size material is equal to the mill kilowatts times the classification system efficiency times the ore grindability times the mill grinding efficiency. And we see that there are two separate active efficiencies at play in a ball milling circuit, the classification system efficiency and the mill grinding efficiency. Now let's look at an example of how the functional performance equation is calculated and how it's used to study a change in the performance of a ball milling circuit. At the Cell Bay Copper Concentrator, a study was conducted to find out about the effect of a change in the grinding media on the performance of the ball mill. A circuit audit was carried out to measure the performance of the mill. During the initial survey, the production rate of new product size material, that is, material finer than 106 microns, was 33.3 tons per hour. This was calculated from the tonnage to the circuit, the size distribution of the cyclone overflow, and the size distribution of the new feed coming into the circuit. The mill power draw was 523 kilowatts as calculated at the pinion. The circuit classification system efficiency was 71%. This was determined by taking samples of the ball mill feed at discharge and calculating the average amount of material coarser than 106 micron. The grindability of the ore was measured to be 2.31 grams per revolution as measured in a test laboratory mill, in this case, a bond ball mill. Since we have all the other factors, we can then calculate the mill grinding efficiency, which came out to be 38.8 kilograms per kilowatt hour per gram per revolution. Months after the grinding media were changed, another survey was carried out. This time, the production rate of a new minus 106 micron material was 30.6 tons per hour. The mill draw was 545 kilowatts. The percentage of coarse material in the mill, or the classification system efficiency, was 72.4%. The grindability of the ore was measured to be 1.43 grams per revolution. The overall mill grinding efficiency increased to 52.9, a substantial increase over the 38.8, and this is directly attributable to the change in grinding media. A second example of calculating the functional performance equation is taken from the Dome Gold milling circuit. The grinding circuit uses 2 stages of cycloning in addition to a lot of water that was added into the circuit because of the jigs. Comparison of the Dome survey with the initial Cell Bay survey shows that the classification system efficiency, as measured at the actual P80 of the survey, was 85.5%. 85.5% of the mill energy was being used to grind material coarser than the P80. Compare that to the Cell Bay circuit, where only 68.5% of the energy was being used. This tells us by manipulating the pumps and the cyclones and the water usage in a grinding circuit, we can increase our efficiency up to as high as 85.5%, sometimes higher. Here's an example of numerous surveys that were conducted at the Tilden Iron Ore Concentrator, studying the percent solids of the mill discharge and the mill grinding efficiency. 16 surveys were conducted over a period of several years. The initial 12 without intentionally varying the mill percent solids, then by increasing and then finally reducing the water addition to the pebble mill. This relationship between the mill grinding efficiency and the percent solids in the mill was determined. It is statistically highly relevant. What it showed was that by reducing the amount of water addition to the pebble mill, the mill grinding efficiency increased. Such an increase provided major energy cost savings. Here is an example of the use of the functional performance equation to study the replacement of standard cyclones with modern high-efficiency cyclones in a sulfide flotation concentrator. The survey data in the first equation shows that the classification system efficiency was 56.6%. With new cyclones, circuit modeling showed that this could be increased to 60.9%, an overall increase in efficiency and circuit production rate capability of 7.5%. In addition to the benefit of classification system efficiency, the cyclone overflow product size distribution was significantly narrower, reducing the amount of coarse particles going to flotation at the same grind P80. Installation of the high-efficiency cyclones took place and the benefits were achieved exactly as predicted. In another study for a gold ore processor, the amount of water being added to the cyclone was varied to create different cyclone overflow percent solids, varying from a high of 50%, which would be typical for a CIL circuit feed, to as low as 10%. We know that by doing this, we increase the cyclone efficiency. And by doing so, we were able to increase the classification system efficiency from the mid-60s all the way up to the mid-80s, even 86%. This showed us that by installing a thickener after the grinding circuit, for example, to deal with all the extra water ahead of CIL processing, that the efficiency of the grinding circuit could be increased by approximately 30%. The thickener was installed, and the grinding circuit significantly outperformed all previous production. There are many examples of the successful use of the functional performance equation in mineral processing plants today. Here is just a short list of some of them. Every one of these is taken from actual plant experiences, and all provided efficiency improvements resulting in major financial benefits for these companies. The functional performance equation is an excellent tool for making improvements to plant grinding circuits. First of all, it is very simple. Secondly, it is very accurate. Thirdly, it clarifies our understanding and quantifies ball mill circuit performance. It recognizes that there are two separate active efficiencies in play: the circuit classification system efficiency and the mill grinding efficiency. And it quantifies them for us. That is, provides the metrics to measure and see improvements. Next, each efficiency is clearly linked to specific plant design and operating variables. The circuit classification system efficiency is related to the setup of the pumps and the cyclones. The mill grinding efficiency is related to factors like the ball size and the percent solids in the mill. Next, this equation provides us clear optimization criteria. We want to maximize the circuit classification system efficiency, and we want to maximize the mill grinding efficiency. And finally, it provides a strategy and a clear plan for plant optimization work. We conduct an audit and complete the functional performance equation. We then look at ways to change the pumps and the cyclones or the operation of the ball mill to improve their performances. We implement those changes, and then we go back and do another audit to see how we've done. The functional performance equation is indeed a breakthrough, a new tool that allows us to better understand, to better measure the performance, and to improve the efficiency of ball mill grinding circuits. We are grateful to McGill University and the many industrial companies who have contributed to the development and use of the functional performance equation.